Hey guys, this is Sai Das, your NPTEL TA for transport process, transport phenomena and biological systems. Yeah, we have done this for a long time now, so I'm gonna give the class 15 minutes to assemble, and if it doesn't, we will start. This time it's going to be 10 minutes because I have a little more to cover, and right. Alright, let's start. So today we are going to look at the mass transfer kinetics of a particularly important um, fluid in another fluid, that of oxygen in water, or air that is present in oxygen into the liquid water. So why is this essential? Because as you all know, oxygen is the terminal electron acceptor of oxidative phosphorylation from prokaryotes to us human beings. So it is important for for everything, but in the context of biological systems, when we talk about it, we can look at it mostly from the typically it is looked at from the engineering perspective, where we choose to grow a certain microorganism which consumes a certain amount of oxygen during a certain unit of time. Now, to understand this further, we need to understand how the oxygen that is typically these bioreactors do not rely only upon the oxygen that's present in the headspace between the reactor and the reactor um, in the between the in the headspace of the reactor. I am assuming you know what headspace means. I don't want to explain such an elementary detail. Now, in bioprocess engineering, we do not rely only upon that. We typically sparge the system with air. So air, as you know, is 21% oxygen, and as a result, we are in effect sparging to a 0.21 mole fraction of oxygen for every mole of air that is being pumped into the system. Now, how does this oxygen from the air, or let's say an oxygen bubble, or oxygen in the air bubble, travels from the air bubble into the bulk liquid medium? So let's look at the journey of a bubble, of a gas bubble, of that of air bubble. Typically, it's gas bubble, but it is typically an air bubble. So this is the interface of the gas bubble, and in the inside of the gas bubble we have 21% of oxygen. This oxygen has to travel through the gas bubble, and there is a liquid film in it. So you should in when you people who understand bioreactors or have seen bioreactors in action, you should be looking at continuously sparged system, and everything is in motion. There are impellers, typically called as Rushton impellers. If people who are interested, go Google it up. So if you look at a typical lab scale or a pilot scale bioprocess setup, everything is in motion. However, at the molecular scale, or at the interface between the gas bubble and the bulk liquid, there is a stationary film of near stationary film of bulk of liquid, which does not have any velocity of its own. So when we talk about this three arrow three, the traversal of air through the gas bubble boundary and between the gas liquid interface, this is called as the gas liquid. This is the gas liquid interface, and this is the liquid film. So through the traversal of air through the gas liquid interface and into the stagnant layer of liquid film that is present around each bubble, and from there, once it crosses this near stationary film of liquid, uh, it goes into the bulk liquid, where there is dispersion because of the uh, because of the impeller action and the movement of macroscopic movement that you actually see. And this air molecule traverses through the bulk medium and it goes to the cell. Now let's take the example of a single cell. We don't want to look at cell clumps. We are not going to talk about cell clumps, or we will talk about cell clumps for a minute, and I just thought of a question right now about that. Now let's say no let's take the example of an individual cell and this oxygen molecule traverses through the bulk liquid now to the site of to the near the cell. Now, even in the case of the cell or any solid particle or any particle that is bound by a boundary, that is bound to be a near stationary liquid film around it. This is how bioprocess works, and all mass transfer resistances are are set there. This is the rate all mass transfer or to put it in a way that doesn't give you a lot. There are certain questions about this in the future previous slide, in the next slide, so I'll leave it at that. Now the gas bubble has to, I mean the air has to, or the oxygen has to traverse through this stationary film of liquid in between the cell and the, this is the film of liquid, and it has to traverse through this liquid film and then into the cell, and then where it diffuses to the site of oxygen reaction. Now this is how it all works. Now this is the text of what I just explained. I'm not going to explain this again. People who are interested can look at the slide. Now my question here is simple. Which of these steps is rate limiting? We have seen all these steps: the traversal from the gas liquid through the gas liquid interface, and through the stationary or near stationary liquid film and into the bulk fluid, and here, and going in and going in. So which is the most important rate limiting step of this reaction? Think about it. That is one thing. And what will be the reaction, or what will or let me put it this way: will it be easier for mass transfer to occur in a cell if it is present in a as individual cells dispersed finely through the medium, or if it is present as cell clumps? That is one question. Let's first answer this question: which of the step is rate limiting? I'll give you a minute to think about it. A minute or two. It's very easy if you look at this diagram. It's very easy to deduce it. It's simple, right? I mean, I think most of you should have got the answer. It is the traversal through the near stationary liquid film that is present in the interface between the gas and the liquid, because it's a gas to liquid transfer. Think about it. That's very important, and that is why this is the rate limiting step in most bioprocess operations. Now that is the first question. Now the second question, the answer. Now the second question is, will it be easier for mass transfer to occur or oxygen transfer to occur if the cells are finely dispersed in the medium, or if the cells are clumped? That's one question. And the second question is, likewise, if the is mass transfer easier to occur if the gas bubbles are finely dispersed as small bubbles throughout the medium, or big bubbles are better, bigger bubbles are better? Both questions have the same answer, by the way. It's a very simple question. I'm not going to give you more than 30 seconds for this, or take a minute. So the answer is simple, right? It's just surface area. The so it's individual cell and smaller bubbles, because for a given volume of cell, or that of gas or air, the higher surface area would result in better mass transfer, right? I mean, it's very simple. So that's about that. Now, so let's look at this process. This whole gas to liquid transfer process diagrammatically here. Now, this is the phase one, which is the gaseous phase, and this is the phase two, which is the near liquid, which is the liquid film that is surrounding the gas bubble. And actually, there's a concentration gradient of the gas of oxygen. From the center. Let's say this is the center of the bubble. This is the end. This is the interface of the bubble with the liquid film. So because of this concentration gradient, the oxygen actually travels from from the point YAG to point YAI. And now there is a concentration difference between the gas of oxygen between the interface of the gaseous interface and the liquid interface, as you can see diagrammatically. And because of this crosses the interface. Now, as I told you, this is the rate limiting step. And once it crosses the interface, and then it has a concentration gradient, it goes down the concentration gradient, and then it goes to the bulk liquid, and the rest of the story. So this is the diagrammatic representation, and from this diagrammatic representation, a set of formulas are taken, and finally moles transferred per unit volume per unit time is given as Kxa or Kla into Xa star minus Xal, or where Xa is the Xa star is the amount of oxygen that a liquid can hold, and Xal is the amount of liquid that's amount of oxygen that's already present in the liquid. Typically, you will see this as KLA is equal to OTR, or the oxygen transfer rate equal to, or the oxygen consumption rate equal to at steady state. Okay, let's not talk about that. The oxygen transfer rate equal to KLA into C star minus CL, where KL represents the mass transfer coefficient of the oxygen from the gaseous interface into the liquid interface. A is the interfacial area of the gas in the liquid film, and XCA star slash XA star and CA star slash CAL slash XAL is the concentrations, as I said before. So it's KLA into C star minus CL. KXA and KLA will be used interchangeably throughout this presentation. So to understand how this formula is derived, please look at the book of Dr. G.K. Suresh Kumar, as well as the lecture, the online lecture videos. Now, I have a question. Does physical parameters like viscosity, temperature, and pressure play a role in KXA or KLA? So typically, see, we are not typically people do not look at KL and try to find out the interfacial area of the gas bubble. It's not happening, right? So typically people look at KLA as the mass transfer. KLA here is the mass transfer coefficient. Now, does viscosity of the liquid play a role? So you don't need to look at all these formulas and stuff like that. You just need to use your common sense. All I need you to do is to map the physical property with what happens intuitively in your mind. Just run that reactor in your mind where the fluid is more, the liquid is more viscous, and then tell me. I want you to visualize viscosity, I want to visualize temperature, I want you to visualize pressure. When I say pressure here, I am talking about the gas pressure. All right, so viscosity is easy, right? I mean, if you the fluid or if the liquid that is present in the bioreactor is highly viscous, first of all, the speed of the impeller will be lower. That is one. And the second thing is that the liquid film that is we talked about the stationary liquid film around the gas liquid interface. Now even the bulk liquid will be relatively much more stationary, because that is the concept of viscosity. So now in addition to the step 3, or the transition of the oxygen molecule from the gas liquid interface into the liquid film, the step 3 that we talked about being the rate limiting step. In addition to that, the journey of the oxygen molecule through the bulk liquid will also become, in some cases, depending upon the viscosity of the fluid, rate limiting, because it cannot travel faster, right? Because it's viscous. That's indirectly the definition of viscosity. um, So what does temperature, what role does temperature play in KLA? Actually, temperature has an indirect effect on the mass transfer kinetics, because solubility of gas depends upon the temperature. You can look it up, of the solubility kinetics of various gases, including that of oxygen, air, oxygen in air, and pure oxygen, other gases like nitrogen, argon, etc., etc. Every gas has a uh, solubility correlation, and you can go look it up. Temperature does affect it. And how does sparging pressure affect? It will increase the KLA, because if you increase the pressure, you are basically saying that you are increasing the flow rate of the uh, higher, when now actually this can be interpreted in two ways, right? If you're going to increase the pressure, um, when I say we are going to increase the pressure, we are going to increase the force of the gas that comes into the fluid. Now, assuming that the flow rate doesn't is not is not correlated with pressure, the the fluid, or more of the fluid will start to flow through the bioreactor. So if you are not controlling the bioreactor with a rotameter or something, typically it is controlled. But I just wanted to make you think, like, what will happen if the pressure increases. If the pressure increases, actually the flow rate increases, if it is not bound by a rotameter or something like that. Even if there is rotameter, if you increase the pressure, the rotameter will automatically increase. Then you need to control the rotameter. The rotameter will automatically increase the reading, thereby increasing showing a higher flow rate. When you increase the pressure in the compressor that drives the bioreactor, so then you need to adjust the rotameter. So without the rotameter, this implies that if you increase the pressure, you increase the flow rate, and if you increase the flow rate, you increase the amount of gas that's available, and thereby the mass transfer kinetics. Okay. All right. Now let's go to the measurement of the how do you measure this KLA in the bioreactor, KXA or KLA. It's used interchangeably, as I said. So the most popular method is the dynamic method. So what you do is, you take a liquid, and then you just sparge it with air. So basically this is the start of time. You keep sparging. First of all, you take it to C star, the amount of gas that the liquid can hold. And after that point has reached, let's assume the start of the x-axis is that point. Then you can see that the rate of, I mean, the concentration does not increase with time, oxygen concentration, which means that it has reached steady state. Now if you stop the air right now, and assume that there is a oxygen consuming species in the liquid. So basically assume that the liquid is a nutrient medium, and there is a bacteria that is growing in that liquid in the bioreactor. The oxygen concentration will come down. Why will it come down? It will come down because the gas is being consumed, right? As I told you initially, that oxygen is a terminal electron acceptor for energy metabolism. So the organisms inside the bioreactor are consuming oxygen, correct? So it will start coming down. Now at this point, the air is turned back on, and then since the now the oxygen uptake, the oxygen transfer rate from the compressor into the bioreactor is greater than the oxygen uptake rate by the organism in the liquid. The amount of oxygen that is present in the liquid, which is at this point CAL, CAL, which is less than CAL star, the amount of the concentration of oxygen slowly creeps back to its final concentration, which uh, you know where the we can say that steady state is reached between the oxygen consumption rate and oxygen uptake rate. Now, so now here, if you think about it, the rate of change of concentration CAL is a factor of two things. Is a factor of the oxygen transfer rate, which is given by KLA into C star minus CL, and the consumption of oxygen by the microorganism. This is the specific oxygen consumption rate and consumption rate per unit biomass, and this is the amount of biomass that is present in the bioreactor. So basically, this is the oxygen transfer rate from the compressor into the bioreactor, and this is the oxygen consumption rate, and the rate of change of oxygen in the system should be the oxygen transfer rate minus the oxygen consumption rate. It's very simple, right? Now what we need to now do is that as I said here, this term CAL dash, if you see here carefully, it will be slightly lower here. That is the that is the steady state assumption. What we are assuming is that at one point of time, when the when there is if you when you keep taking readings at different samples of time intervals using you know uh, a dissolved oxygen probe, it will start to equilibrate at or near the C star. And why does it not equilibrate at C star? It's because there is a consumption of oxygen by the um, you know by the species that is present in the system. Actually, if you think about it, here we are assuming so this is not actually this may not uh, this can be considered as C star, assuming that we first start out with the clean fluid, and then we typically add but that doesn't make sense. What we can say is that we add a preponderantly high amount of gas in the liquid, so that it attains C critical, and here we decrease the flow rate so that it attains a steady state which is lower than the C critical. So but that apart, you can say that steady state at steady state assumption there is no further change in the concentration of the concentration of the oxygen that's present in the liquid. You can just leave out the C star and CAL dash debate for now. Um, all we need to understand is that at this point the amount of oxygen that's transferred into the reactor is it matches exactly the amount of oxygen that's consumed by the microorganism. So so at this point of time, the left hand side becomes 0, QO into X equal to KLA into C star minus CL dash. So that this is the concentration at which the steady state is reached. And then you substitute 1 in 2 or 2 in 1, and then cancel all the common terms. We get this dCal by dt equal to KLA into C dash AL minus CAL. So C dash AL minus CAL, if you think about it, uh, it's simply the in other way, this CAL dash. What is C star? If you think about it, C star is the oxygen transfer rate in a pure liquid. Ca dash or CAL dash is the oxygen transfer. No, sorry. Let me rephrase it. C star that we saw here, right? This one is the amount of oxygen that is that saturates a pure liquid, which does not have any consumption kinetics. Ca dash is the saturation concentration of oxygen in the presence of a consuming organism, oxygen consuming organism. So CAl star and CAl dash are, they are not same, but they are similar. So we had this question here, right? Why the this and this. So that's the difference actually. Now fine. So we have a differential equation. Now how should we proceed further? Any ideas? Any brain waves? Of course, we need to integrate, but what is the assumption under which we can integrate? That is the question. Or the question can be rephrased as this: what should be the condition in the reactor at which DCAL and DT become unitary? Then thereby we can take DT down to the other side and this turn down, and then we can integrate. That needs to be a critical assumption that we need to make. I will show you this also. You can think about it. So when you rearrange it, it will become DCAL by CAL dash minus CAL equal to KLA into DT. Now what should be the assumption for integration? How will you integrate it? Integration requires some consistency on the equation, right? So for a given condition, CAL dash is going to be constant. It's just that CAL is the CAL will become when we integrate it, it will become the lower and the upper limit, or depending upon which part of the curve we integrate, it becomes the amount of oxygen that's been what is the area under the curve here? Concentration. So basically, concentration is number by volume into time. Number by volume into time. So this one. So if you integrate it, that's what we are going to get. And moles stands for per unit volume per unit time. But that's fine. That's a side note. But okay, I'll give you the answer. So see, when we say DCAL equal to or DCAL by CAL dash minus CAL equal to KLA into DT, then put the integration sign, we have to bring out this KLA out, right? For that, KLA has to be constant. Or in other words, the critical assumption here is that we need to assume that KLA does not change with time. It is not necessary that KLA should not change with time. And there is a question about that for you to think about. So when you integrate, you get this, and then if you plot ln CAL minus CAL1 and CAL2 are the two arbitrary time points between or think about it as the delta or the time intervals during which you measure the various parameters, not the various parameters, the dissolved oxygen concentration, that's all you will measure. And there is something I need to tell you about how to measure dissolved oxygen. What is the principle by which dissolved oxygen is measured? I'm not going to tell that in detail. I want you to give I want to give you a glimpse, and interested people can go Google it. So if you're going to plot this with this, you're going to get a straight line and the slope is going to be KLA. From this we'll get the KLA, assuming that KLA is constant and doesn't change with time. Now I have a question for you. During an experiment, if the it's not FF, it's if the liquid is not well stirred, you know, can we use the KLA from KLA value from the graph, or can we use this method? I'll give you a minute and a half to 2 minutes for you to think about it. I've already given you the answer. All you need to do is to just walk back into what I just said, and what you, and then juxtapose it with what you think will happen if a liquid is not well stirred. It's that simple. It's simple, right? I just told you that the key assumption that we make here is that KLA is constant. KLA doesn't change during time, and if the liquid is not well stilled, we cannot make that assumption, right? Sometimes, if the stirring is irregular, it's not particularly well stilled. Sometimes KLA will be up, sometimes KLA will be down, and it doesn't change. It changes with time, and we cannot use this method to find it out. And okay, now coming to the question of how you find out the dissolved oxygen concentration. So dissolved oxygen concentration is found by using something called as DO probe, dissolved oxygen probe. And there are two types of dissolved oxygen probe. One is the electrochemical probe and one is the polarographic probe. The electrochemical probe uses the good old principle of electrode kinetics, like how okay, to give you a glimpse, oxygen diffuses through a film into the into the chamber, and then from there, it reacts, and it reacts, and it gets connected to the cathode, and there's a small current pulse, and that pulse is being recorded, and that analog signal is converted into what you see in the digital meters. Uh, that gives you the dissolved oxygen concentration. They are already calibrated and given to you. So that is of the electrochemical thing. Polarographic uses certain optical properties of oxygen to measure its dissolved oxygen concentration. And I would leave it to interested readers to understand how these two probes work further. If you want to know further, I would encourage you to go and read about this. So that's about that for today. And in addition to Dr. G.K. Suresh Kumar's book, there's a book called Bioprocess Engineering Principles, and all this some of the data has been taken from that. It's an excellent book for bioprocess, to understand the basic principles of bioprocess, along with bioprocess engineering. That's another bioprocess engineering book written by Schuler and Kargi. That's also a very good book, and I would suggest you read both of these books uh, to understand. This bioprocess engineering principle is much more deeper in terms of the topics covered than Schuler and Kargi. And I would suggest interested readers to go and look at this book. It's a really, really good book. I would suggest you read the interested sections of the book, you know, back to back. It's a nicely written prose, and so that's about that. We have come to the end of today's lecture. We will wait for, as usual, nobody has come, nobody has turned up. I guess people are watching the video online, hopefully. So we'll wait for another 5-10 minutes to see if anybody magically turns up to ask a interesting question. Are you people watching the videos? I hope you are. Take some time to make these slides for you guys. You know. Anyone? Anyone? Nope. It's just me. Hmm. Still I am legend, huh? Okay. Alright then guys, that's it for today. See you in the next session. Bye bye.